A flamingo standing on one leg seems serene, almost meditative. For decades, the simplest explanation was thermoregulation. A bird loses body heat through its extremities, so tucking one leg up cuts that heat loss surface area in half. This makes perfect sense in cold water, except they do it in warm water too. They even do it on land. This simple answer, while partially true, obscures a far more elegant and counterintuitive mechanical truth. The real question isn't about heat, it's about energy. Standing requires muscular effort to fight gravity. So how could using one leg possibly be less tiring than using two? To solve this, researchers Young-Hui Chang and Lena Ting didn't just watch living flamingos. They used cadavers. They discovered something remarkable. A dead flamingo could be positioned on one leg and it would stand, perfectly stable, requiring no external support. It was a purely skeletal trick. They called it a passively engaged gravitational stay apparatus. It sounds complex, but it's beautifully simple. When a flamingo shifts its weight onto one leg, the arrangement of its joints creates a natural, stable lock. The knee is high up inside its body, and what looks like a backward knee is actually its ankle. The forces align in such a way that gravity itself holds the leg straight. It's like a camera tripod that is most stable when its legs are fully extended. The flamingo doesn't need to flex muscles to stay upright, it just needs to exist. Actively trying to stand on one leg requires more effort to disengage this lock. Every moment you are standing still, your body is waging a tiny war against gravity. Your postural muscles are in a state of constant isometric contraction, burning through ATP just to keep you from collapsing. This is muscle fatigue at its most fundamental level. Flamingos, by locking their joints, effectively opt out of this war. Their skeleton bears the load, not their muscles. This allows them to sleep while standing for hours, expending almost zero energy on posture. It's an evolutionary cheat code against the constant energy tax of being a large, upright creature. This principle of passive mechanics isn't unique to flamingos. Nature prefers an elegant physical solution over a costly biological one. Consider a bat hanging upside down. It's not actively gripping the branch. Specialized tendons in its feet lock automatically under the bat's own body weight. It takes more energy for a bat to let go than to hold on. Or look at the powerful nuchal ligament in a horse's neck, a thick band of tissue that passively supports the weight of its heavy head, saving its muscles from the constant strain of grazing. So, if this passive lock is so efficient, why do flamingos ever switch legs? Why stand on two legs at all? The complete answer remains elusive. It may be to manage long-term stress on the joints, something a cadaver can't tell us. It could be to allow blood to recirculate properly after hours in one position. Or perhaps the original thermal reason still plays a part, and the two behaviors work in tandem. The simple act of a flamingo standing in the water is a quiet demonstration that in biology, a simple question rarely has a simple answer. Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.